You're right, the title is different because here I have just subtitle that most likely expresses our motivation in this study. This study was done with my good friend and advisor and teacher, Professor Samko, and it just published and to be published in Mathematical Notes this month. And well, we asked a question: what about the theory of grand spaces in the case when we focus only on holomorphic functions? Because holomorphic functions much better; they occupy a small space in the space of measurable functions. They possess some nice properties, and you would expect that in the case of holomorphic functions, you can have some more precise conditions, some different conditions, and it is okay. So, but when we focused ourselves on holomorphic functions, we came up with the theory of aggrandization for a general set of measurable functions. So my talk will be divided into two parts. First, I will be speaking about a general theory, because once we realize that in any case we have to apply general instruments, so it's worth to prove some facts in the more general settings. So my talk will be divided into two parts. First part will be devoted to the issue, to the problem of aggrandization in a general normed space. This may be at now it may be the most general statement of aggrandization of spaces, and then as a second part we will apply this result to a particular case of some holomorphic functions. But first, of course, I will give some ideas of grand spaces and aggrandization. So grand spaces, actually, people say that grand spaces appear in papers by Carlos Bordone and Tadeusz Iwanets, but actually some researchers before that studied similar spaces. But anyway, people say that they appear in papers by Carlos Bordone and Tadeusz Iwanets, and these grand spaces appear from applications. How? When you study partial differential equations and take integrals to some power p of some constructions, somehow if you have a not a nice domain, you want to go to a nice domain like half plane or circle or something else. So you do change of variables. You do change of variables inside of integral, then you have Jacobian, and it happens then after this, because you don't have maybe nice estimates for Jacobian, the construction inside the integral becomes non-integrable already with the same power p. That's how you need a bigger space. Of course, you can, if you are on a bounded domain, you can take, instead of p, you can take p minus epsilon, and this function will be integrable with this exponent, but then you will be far away from LP. So the idea is how to get a bigger space, which will be a little bigger, infinitesimally bigger than the previous space, so as not go far from the initial space. And that's how they came to the so-called grand space. And well, here is the definition. You see, they take p minus epsilon, multiply by epsilon to some power theta, and they take supremum. First of all, this already not separable, for instance, space. It's pretty bad now, but still it's good for the study. They also provided with equivalent norm. Sometimes this norm is better, but still you have to calculate the non-decreasing rearrangement, etc. So this norm sometimes appear to be difficult to handle with, because you have to take supremum and calculate all this construction. And of course, I'm speaking, this is just restriction, just technical restriction. You can think just measure is just one, you can think that measure is bounded. Measure 1 equals is necessary only for technical purposes to have Gölder inequality with constant 1, you know. But of course, the general theory of grand spaces before the papers by Samkov was developed only for bounded domains. Only for bounded domains, because just when you decrease the exponent, you get bigger space only for bounded domains, Okay, so here is the definition. I will come back to the definition again, and let me see. Here, well, of course, grand space is bigger than LP space and is smaller than any LP minus epsilon space. Of course, if you have grand space, you have also small space, which is inside LP. Small space you use for Gölder inequality. It is associated space. I will not be speaking about small space, but just to let you know. Of course, there are some more connections with Lorentz space, with some other spaces, but I will be speaking about these issues. The most important is here that grand space, as I said, it's bigger than LP, but it's smaller than any P minus epsilon space. Okay, as an example of a function from grand LP space, you can take just a simple example. You can stay at interval from 0 to 1. From 0 to 1, so dt over t equals to infinity, as you know. So 1 over t to the power 1 over p belongs to grand LP from 0 to 1. Grand LP. But of course, this function does not belong to LP. Yeah, just a very simple example of a function that belongs to grand LP and does belong to regular LP. Okay. Well, for instance, also to have an idea of what is the grand space, for instance, in the paper by Saludin Marhadjiyev, also before in Alberto Fiorenza papers, they calculated the fundamental function. Fundamental function is a norm of characteristic function in the space. It's very important for rearrangement and variant spaces. On basis of this fundamental function, you can tell many properties. So for LP space, fundamental function is just eta to the power of 1 over p. For the grand space, you have this addition, log addition, so you can imagine what's the difference between LP and grand LP space. Okay, well, now, since I've been speaking about holomorphic function, you can ask me, okay, you have an example of measurable function, but maybe in case of holomorphic function, the situation will be different. Maybe there will be no difference between grand and usual space of holomorphic function. For this, we have example here. It is known that the AP is just for Berman space. Berman space is intersection of LP with holomorphic functions. Okay, so always AP, always A calligraphic means Berman space, which is intersection of holomorphic function with the initial space. In this case, LP. So this function, we know that this function belongs to AP. It means the LP norm is finite, if and only if this is true. But yeah, let's see. But what we proved that this function belongs to, with lambda equals 2 over p, belongs to grand space. So this function belongs to grand space and does not belong to initial p space. Okay, and this for theta equals to 1. For theta greater than 1, we have this also example with this logarithm function. This log function, this function belongs to grand space and does not belong to regular AP theta, AP space, does not belong to regular AP space. So we have examples of some simple holomorphic functions, like in this case, that means that our study makes sense. Okay, well, that's what I probably should start with. I already named Tadeusz Vanitz, Carlos Bordone, Greco, Di Fratta, Fiorenza, Garagioff, etc. So many persons, so many researchers studied the theory and developed theory of grand spaces, generalizations, Morris spaces, Mori grand spaces, Orlich grand spaces, Mori Orlich grand spaces, many different generalizations, variations, but all this about bounded domain. All this about bounded domain because the idea of the gradization is just to subtract epsilon and make the space bigger. And this works also only for bounded domain. Later, Samko and Umarhadjiyev, they, well, I'll come back to this question later. Let's see. Later, Samko and Umarhadjiyev developed a theory. They found a way how to aggrandize space in case of unbounded domain. They applied a different idea. They instead of subtracting epsilon, they inserted a multiplier, certain multiplier in the integral that depends on epsilon at x supremo. And in this case, they managed to construct a whole theory for unbounded domains. Okay, as far as I know, only few people after them followed this idea because it's kind of recent. Umarhadjiyev defended his doctoral thesis in our university 2017. So this kind of very recent studies. But then they go further with Raffaele Umberto. He applied same approach also for bounded domain. In a sense, they developed a theory of localization. I will speak about this later. The only issue I wanted to point out that we will use this approach to construct our ideas, to construct our generalization that is different from the classical one, from the one that was, yeah.
But in the case of bounded domain, this approach coincides, gives the same space.
It's a different, yeah, I cannot say this because this kind of different space. You have to prove in every particular case. The idea is that you want to get a bigger space, and that is usable for your
extension of the backspace.
Yes. LP.
No. For bounded domain, they developed the theory of local grand space. So they aggrandize with respect to certain curve. For instance, in case of Carlos Bordone de Oshevane, they take supremo over whole disk. Samko and Umarhadjiyev took a line and consider grand space which are grand only for these points, and they are regular for the other points. They call it local grand space, and the theory is called local grand space. That's what we use. Okay, so it's a different issue of organization. If you want to coincide that you have to take instead of curve, you have to take all points. No, but I'm not sure that it's possible. And what about complex analysis? If we speak about grand spaces, complex analysis in classical setting, that I can also only name these papers. Also with Samko, in this paper I will be speaking about. I'm speaking about right now. It appears in mathematical notes. It's written, submitted, but it's already, I think, will be published in a couple of weeks. Already published. Okay. Well, let us come back to the classical definition and compare what we propose instead. So here is the classical definition by Tadeusz Iwanets and Carlos Bordone, and here it's just a particular case, just to show you our definition. So what we do, we don't subtract epsilon here, which is good. We put some weight here, and why I'm saying, I'm not completely sure that this definition is much better than this. I'm not saying that this is much better, but in some cases, when you consider norms of operators, it might be easier to consider norms of operators in weighted spaces instead a sequence of norm that depends on b minus epsilon.
What does it mean, this sign?
Equivalence up to a constant, yes. Equivalent up to a constant.
In this case, you obtain the same.
Yes. This case describes the same space. Yes, exactly. Yeah. But here, of course, you can take an arbitrary function. This is on this just kind of model function. You can replace by a general function, which we call aggrandizer. This is important because roughly speaking, we can take an arbitrary, absolutely arbitrary function. You have the same space. So you can take whatever you want in your particular situation to calculate the integral to define the same space, of course, up to norm equivalence. Well, I need the definition of Orlich to proceed with. I need definition of Orlich-Matuszewska indexes, but actually I need these definitions restricted to certain case. I will also, okay, let me put here, come back to this formula. Sorry, back. What we have here, a function a, I will call aggrandizer, that makes the space grand space, okay? And I will denote it A. Basically, what I need from A, I need to introduce this Orlich-Matuszewska indexes because in our case, this function is quasi-monotone function. What this means? That means it's the following, okay? So in this case, the lower index is like this, the upper index is like this. I also will use a notion of doubling condition for a function which is written here, phi at the power at the point to t less or equal constant phi of t. That's what I need.
Almost increasing means increasing
Up to a constant. A constant before the less or equal constant times the other. Okay, so now let me start with the definition. I have a domain. D diameter of this domain, a metric, d small. Okay, I introduce a distance. I take a set f subset. You can imagine is as a curve here, f. So basically, the set f is the set toward which I will aggrandize the space. So if I take a point here that I measure distance between points in this set, this is distance delta. Well, as I said, we develop theory for an arbitrary normed space of functions. To each space, given a space, that's what I want to aggrandize. I take just arbitrary normed space. I want to make an aggrandized space. I associate to each x, I associate the space xw. We can call it weight, but basically it's more weighted space. We speak about weighted space if we have kind of like function f times some weight belongs to some space. In this case, definitions is general sense. It's just a couple of, it's just a set parameterized by omega. I have no idea how omega enters into the norm. It can be in the norm in a very, very general manner, okay? So it's not good to call it weighted space, but I will call it weighted space. But it is just a general couple of space x and function omega. Okay. With the only assumption, I still need one assumption, which is natural. If we have one weight is less than another, then it's natural to ask then the same will be true for the norm. This is just only assumption I have for now. So having defined this, I take the set f, I take the space x, and I write the construction x g for grand, f for the set to which I localize, a small for aggrandizer, and theta is just general parameter. And I construct this norm. So take supremum, this norm of function in this weighted space. Here I have a composition of my aggrandizer with a distance. I have a condition that a of 0 is 0, okay? A of 0 is 0. So a composition with the distance will be 0 on this curve in particular case. And of course, I immediately have this embedding because of this assumption. And you see that I don't use L here in definition, because actually we don't care about L, because again, up to equivalence norm, you have these inequalities. So you may not care about this L. You can just take a very small L, as small as you want, okay, to take supremum over 0 L. Okay. Well, let me illustrate some useful properties. Well, again, here, this theorem means that you can aggrandize only in a small neighborhood of this set. You don't have to calculate supremum over all set. You can take this grand norm over on a subdomain, which is small neighborhood of this local set, and the rest you can take the regular norm. Sometimes it's useful because sometimes you want to simplify calculations and not to calculate supremum over all domain, but just calculate supremum. Say I can take a ball here, put inside a ball, I can have a nice geometry, etc., and more simple calculations. What else? Well, also very useful properties, because I can change one aggrandizer by another, and I have this inclusion. Okay, and also if the space is smaller than f1 is smaller than f2, then
It does not depend on alpha.
which alpha? No. Alpha positive. And the constant might depend on alpha. Alpha is positive. Of course, if you aggrandize with respect to a bigger curve, then you have a bigger space. It's clear. And we also use this property later. This is just general properties. This is very powerful theorem. You can raise your aggrandizer to arbitrary power, to arbitrary positive power. Okay, you have some calculations, you end up with some formula, you have your aggrandizer in a certain power, you don't like this power, you just cancel it. Okay, it's very useful. Up to norm equivalence. And also, if you have two agrandizers with lower Ulrich-Matuszewski index is positive, then these spaces just coincide up to norm equivalence. This means that you can replace one by another with this condition. Okay. Well, now it was a general theory. Now I came to also important question, whether this is a real ground space, whether I can show you an example that belongs to initial space and does not belong to the ground space. This is I can prove this under these two simple conditions. Well, this is also natural. If you have bigger radius, then the norm of characteristic function must be bigger. And if you have, instead of weight, if you take a constant, then it should be somehow relevant to the initial norm, because constant should not influence your norm, okay, in this sense. This works for many known space, of course, by just calculations, but for a general space, we don't know. So we impose this condition. For a Lebesgue space, it's just a simple constant like this. Okay, so these are very mild and very natural conditions. These conditions works for many natural spaces. And well, this function, what I have, I take norm of characteristic function with radius rho. I take this norm in x, and x constructs the new function. So this new function I use to define f0 function. It's a function nu x, the point distance between x0 and x. And in this case, as I said, I can restrict myself to the case when f equals to x0 only. Okay, so I demonstrate this theorem for the particular case of one point set. Okay, so this x0 is exactly the set f. And well, because of course I assume that the norm of x is absolutely continuous. That means that when I squeeze the radius to 0, this should go to 0, but this doesn't go to 0 because of this inequality. This contradicts our assumption. So this function does not belong to initial space, but the same function belongs to ground space under this condition. Well, this kind of complicated condition, if you if this function nu of x possesses the doubling property, then you can simplify this condition like this. So under this condition, the initially defined function f0 belongs to aggrandized space and does not belong to initial space. So we have an example of such a function. Okay, now this is all about, this is all about a general theory. Now I come to the second part of my talk. How much time I have?
Excuse me, wait a minute.
1 minute? Okay.
No, at least 5 minutes.
Okay, 5 minutes, I will try to. Okay, then, well, I skip definition of ground space, or I skip definition of, well, just I need to give a definition of Morris space. This is because you know definition of Lebesgue, you may not know definition of Morris space. You have a function phi, this power r to the power 2 or pi, and you take a norm of f in Lebesgue space intersection with the disk with center at z and with radius r. Well, I do aggrandization according to our scheme, and I compare this aggrandization with a classical aggrandization. So this is a theorem. Under this very mild condition, our localized space inside classical ground space. And if any of this condition holds, then classical ground space inside our space. So, of course, if all conditions satisfied, that we have criteria. If you see, for instance, if you point attention to this condition, you can understand here delta is arbitrary. So I cannot imagine what may happen that you cannot find such a delta, because you can take delta as small as you want or as big as you want to cancel whatever you have here, you know, to make this integral convergent. I don't have in mind an example why you cannot find the case in which you cannot find this. So you see, this is very mild condition, and also here eta is arbitrary. You can take arbitrary close to zero, very big eta as you want to satisfy this condition. So you can move these parameters to make this condition satisfied. Okay, so in particular case of power weight, we are speaking about weighted space. You have this simple condition. Also, gamma is here, but delta is arbitrary, and up to this condition, you can easily see that with 99%, I'm sure that you almost always can find parameters to satisfy this condition. And for instance, here, if you take a grandizer with Matuszewska-Orlich index, lower Matuszewska index positive, then you have no condition at all. For every aggrandized space, you have coincidence with classical ground space. This means you can take every function with just this condition. It means that you can construct your DOM as you wish. You can take such a function that is good for your calculations. And the same applies for Morris space. I will not repeat this issues, similar conditions, also parameters. Also, you can vary parameters delta and beta, etc., etc. And most likely, I stop here.
Yeah.